Hey guys, welcome to this another day of lead code solving. Today we're going to solve this question where we have to find out whether a linked list has a cycle. But it's easy because there are very specific conditions. First of all, as we can see here from the examples and this position thing, it basically tells us that if there is a cycle, then it's only going to connect the node specified in the position index with the tail node. So we're never going to have a cycle in between the linked list. So that's one information. The other thing is we might not have a cycle, and that during that time the position is going to be -1. Now you might say that, okay, well, just do a check for position value, and that means we either have a cycle or don't have a cycle, because that's what we're supposed to return, right? But it's not that simple because they're not actually giving us this position value. All they are giving is a linked list, and this just basically tells us where the cycle exists and with what node, so that we can test our own code. So they're saying that we can solve it in O1 time, but I really don't know how. I guess it has something to do with hash maps or hash tables. But right now, I'm just gonna try and solve it algorithmically because that's all that's coming up in my mind. So obviously, one way to solve it is we could have two iterators in the linked list, uh, and run through the list. So if in a linked list which does have a cycle in this specific question, it means that no node will ever have a null for the next node address, right? Because the list will never end, because the cycle, if it exists, it will only exist with the tail node, right? So uh, that means we can first of all iterate through the list somehow and have a condition where if we do have a null value for the next node, we return false because that doesn't have a cycle. And other than that, we can have a fast iteration, which basically jumps two nodes ahead, and a slow iteration. So if there is a cycle, which means there's no null at the same time, the fast eventually runs in circles faster than the slow, and both of them end up having the same address at one specific point, right? So if that ever happens, then that means we do have a cycle. So that's the algorithm I'm trying to think of, and it probably won't be as good as O1. It's probably going to take linear time. In certain situations, it might even take longer than the number of nodes we have on the linked list, but it's probably going to take linear time and not more. Okay, so it's definitely not going to be integer because these are going to be iterators. So let's just declare them. So list node so that we can iterate through them. Fast to jump two nodes ahead. List node low to move to the next node. Okay. So I guess if fast dot next is equal to null, or slow next is equal to null, then we return true. Then we return false. Otherwise, we return true. Which means that a node is because we're okay. So we're trying to increment fast, right? Else um fast is equal to fast.next slow. Oh, also, let's think about what type of algorithm I am writing right now. So it's clearly not a greedy approach per se, because like we're not completely sure of one sub solution and moving on to building on it. It's not a divide and conquer approach. I don't think a divide and conquer is appropriate here, anyways. I can't think of any dynamic programming approaches either. So I guess this is just a normal algorithmic approach where we just have two pointers to iterate through the list and until they match up. If they do, that means the cycle exists. If they don't, and we hit a null, that means the cycle doesn't exist. And until then, we keep moving on. Mm, so dot next. We actually want to do this until oh my god, look at the indentation. We want to do this until fast equals slow. Until fast does not equal slow. Okay, got it. So what we're doing here is we have two different addresses, right? Fast and slow. So fast is going to start with head.next, right? And slow will start with head. Okay. So after initialization, we begin the loop until a cycle is detected. If either of them show signs of a null index, we just cancel and return false because null exists. Because null is not supposed to exist, because as per this question, if a cycle exists, it will only exist in the tail node, which is the only node which is supposed to have the null value for the next node, right? So if null exists, we just close it down. If it doesn't exist, then we keep iterating until fast eventually equals the same address as slow. I don't think it matters that fast is jumping a node ahead and already starting ahead, whereas slow isn't. So I think we might need more cycle of iterations, but eventually we're bound to equal this at certain point if a cycle does exist. Okay, and if it does exist, we fall out of the while loop and we return true. And oh, and another thing, I also thought about a situation where, you know how we have linked lists implemented in Java API, and we have these bunch of um, uh, with these bunch of functions that help us to get useful information like the linked list dot size and stuff like that. So I tried util so that I can get the list dot size. First I tried linked list, and then I wanted to get the size, but it doesn't return anything. And then I tried util to get, because I thought this may have been implemented using the list class and not the linked list class, but even that didn't work, which means that they have smartly coded this linked list manually and given us the definition, which is why it has a list node class, which is not the same as the Java classes for a normal list or a normal linked list, which therefore means that we can't use a size method on this, and rightfully so, because if we did have size, we just go to the end of the, we just go all the way, we'll just iterate all the way until size minus 1, or maybe size, and check if that node has a null value or not, because if it does, we have a cycle, or if it doesn't, we don't, right? So that would have been an easy linear time solution. We just had to iterate through to the end of the linked list. But because this is manually implemented and not a Java implementation, we can't use those functions, which means we can't get the size, and we still have to find out whether the tail node actually has a null value or whether it just loops back. And I can't think of a constant time solution. It probably has something to do with hash maps or hash tables. I can't think of, like I said, I can't think of greedy algorithms or any other approaches. So this is the only thing, and it's probably expensive. But okay, let's run the code. Okay, cool. Let's try something else. What if we have a test case where, okay, let's cut this. -1. Null pointer exception. Yeah. Oh, so we want to check slow.next is equal to null first, right? So if slow.next is equals to null, then we don't have to check fast.next. We only have to check fast.next.next if slow.next is a valid value. If it already is equals to null, we won't even check the second one, we'll go into false. But if it is not, then we should be allowed to check fast.next.next. And then we won't have a null pointer exception. So let's run it again. Okay, cool. It seems to be operating fine. So let's just, all right, never mind. Let's just submit this. It's probably a really bad solution. What? Okay. What if we have an empty list, right? If list is empty, if head is equal to null, return false. Cool. Sorry, submit. What? Head is equal to null. We're already checking for head. Why not? Oh, right, of course. Of course. Depends where you put it. How about now? Also, The reason why we have three checks is because either head might be null or head.next might be null, and we need to check this before we assign fast is equal to head.next, right? So we need to check for this. And since fast is jumping to ahead, and we also need to make sure that they don't. Actually, we could just implement a do while, honestly. We could just implement a do while. How about we should do that. Yeah, let's just implement a do while. That's just way more organized. This is a do while loop, and fast will also be head. Okay, cool. And we won't need this either. Okay, if a list is empty, obviously we return false, or has an early ending, then we return false. If that's fine. If we have the first two nodes, then that means we either return false or we keep going, right? Rightfully so. And by the time we complete the first iteration of the do while, fast is no longer equals to slow, so this should keep running until we actually have a circle. Okay, cool. Let's try this. Wait, what? Mm. Oh, fast is jumping. Fast is jumping twice every time, so we need to check for the initial value too. Next is equal to null. Coolio. Got it. Okay, let's do this once again. Head, null, return false. The next one, null, return false. Start from the same position and put a do while loop. If slow.next is present, only then update it. If it's not, then return false. Because fast runs faster than slow and it's jumping twice every time, we also need to check the node in between, and that's exactly what we're doing. And if both of them exist, then we update fast too. We jump twice if both of them exist, until fast equals slow and we return true. Let's do this. Faster than 100%. And they're telling me that there exists an O1 time. Okay, all right. That's cool. Okay, so let's figure out the actual solution. There you go, approach 1 hash table. And this is on time. 2 pointers. Space complexity is 01, my one. This is the one that I used. There you go. Yes, you don't have to check for slow if you're already checking for fast, right? Or yeah, because fast has covered everything that slow is yet to cover. So you don't really have to check for slow. You just have to check for fast. Cool. So this is the one. And they started 1 ahead for fast. That's fine. I used a do while loop, but that's the same thing. And you don't need an else statement, but that's fine too. And then pretty similar. Pretty similar. Yeah, rather than having 2 if statements, I could have just had like a or right here. Okay. Still on. So where's the O1 solution? Oh, approach 1 is O1, but it has space complexity. Got it. Need to study this. All right, cool.